And today we have the great pleasure to have an IGBT distinguished lecturer as a guest speaker. The lecturer is Professor Makoto Takamiya. And Professor Takamiya received his bachelor, master, and PhD degree in electronic engineering from the University of Tokyo in Japan in 1995, 97, and 2000, respectively. In 2000, he joined NEC Corporation in Japan, where he was engaged in the circuit design of high-speed digital LSIs. He joined the University of Tokyo in Japan in 2005, where he is now a professor of the Institute of Industrial Science. And from 2013 to 2014, he stayed at the University of California at Berkeley as a visiting scholar. His research interests include the integrated power management circuit design for wireless powering and energy harvesting for wearable and IoT applications, and the digital gate driver IC design for power electronics. And this is also the topic of today's talk, which is titled Injecting Digital into Power Electronics. So Professor Takamiya, the stage is yours. Thank you very much for coming and giving us a talk.
Yeah, thank you so much for the introduction. I'm very happy to have a chance to give a talk virtually in Graz University of Technology. I'd like to thank Professor Bernd Deutschmann of Graz University of Technology for arranging this seminar. Today, I'd like to share with you injecting digital into power electronics. In my talk today, mainly I focus on the programmable digital gate driver IC for power transistors. This is the outline of my talk. First, I will introduce the vision of power electronics 2.0. Then, I will introduce the digital gate driver IC. Next, I'll show the degradation estimation of IGBT by machine learning of gate waveforms. Finally, I briefly show the 500 megabps digital isolated IC circuit design. I'll close with a brief summary. The power semiconductors are widely used in application of photovoltaic, wind electricity, and automotive and home appliance applications. So my talk today is an IC design related to power semiconductor. This figure shows the various power transistors in terms of the switching frequency and the output power. In my talk today, I mainly focus on IGBT because IGBT is used in a variety of applications, including automotive and high power inverter applications. Then before starting in gate driver IC design topic, I will introduce the basic of IGBT. IGBT is an insulated gate bipolar transistors. And IGBT has three terminals: collector, gate, and emitter. And when the gate to emitter voltage VGE of 15 volts is applied to the gate, and when the collector to emitter voltage, for example, 500 megavolts is applied, the large collector current flows. This is the example of IV characteristic of IGBT. When the gate voltage of 15 volts is applied, for example, 200 amp collector current flows. An advantage of IGBT is high voltage rating. That means high voltage rating of VCE and large current because of the bipolar transistor. And good point is a voltage drive because it is MOSFET. So IGBT is a combination of MOSFET and bipolar transistor. The right figure shows the cross-section of IGBT. Current flows from the collector terminal to the emitter terminal. This figure shows the equivalent circuit of IGBT. IGBT is composed of the NPN MOSFET and PNP bipolar transistor. This MOSFET is turned on, large current flows from the collector to the emitter. Next, I'll introduce a vision of power electronics 2.0. Now, the AI and IoT, two big waveforms are coming to every industry. AI and IoT waves. So power electronics must introduce AI and IoT technologies to enhance the reliability and performance of the power electronics. And when IoT and AI are included in the conventional power electronics, the power electronics will become a next generation of power electronics. In my talk today, I called it the Power Electronics 2.0, PE 2.0. And including the IoT and AI means injecting digital into power electronics. So this slide explains the vision of Power Electronics 2.0. Actually, it is IoT connected and AI controlled power electronics. For example, sensors and programmable hardware are included in a power devices or power modules, and they are controlled by the ICs. And sensor data are transmitted to the cloud by using IoT. And the major data are analyzed by AI on a cloud. And analyzed results and optimal parameters are given to each user by using IoT. And by using this scheme, customer-tailored service may be available in Power Electronics 2.0. So this is my vision of Power Electronics 2.0. So this slide shows an example of future application enabled by the Power Electronics 2.0. For example, in electric vehicle application, by customizing motor driver IC, the motor manufacturer and car users are directly connected by IoT. And by changing the parameter of the motor driver IC, the cruising distance may increase depending on each user year by year. So this is the advantage of PE 2.0, combining IoT and AI technology. So gate driver is a key block to achieve the vision of Power Electronics 2.0. Gate driver is the first block to interface the low voltage world of the microelectronics and high voltage world for the power electronics. Microelectronics includes the IoT, big data, and AI world, and also include the controller for the power electronics. Typically, gate driver operates at 15 volt. So gate driver is a key block to bridge the large voltage gap between the low voltage world and high voltage world. And gate driver is also a key block to achieve the Power Electronics 2.0. So the gate driver is an interface between the power electronics and IT world. And in my talk today, I I'll introduce three topics. The first is digitally controlled gate driver IC and automatic optimization of the gate driving waveform to reduce the switching loss and switching noise. Then I'll show you the degradation estimation of IGBT by machine learning of gate waveform. Finally, I'll show you the high data rate isolator, 500 megabps digital isolator IC, to achieve the digital gate driver IC. Because digital gate driver requires high data rate digital signal for controlled digital signal. First, I'll talk about the digital gate driver IC and the automatic optimization of the gate driving waveform. And this slide compares conventional gate driver and proposed digital gate driver. In the conventional design, gate driver is just a CMOS buffer circuit operating at 15 volts. And gate driver is connected to the gate of IGBT. And by giving the gate waveform between 0 volt and 15 volt, gate driver controls the turn on and turn off of IGBT. And to control the gate driving, gate resistor RG is manually tuned on PCB. This is conventional design. And the right figure shows the proposed digital gate driver. In order to control the gate current IG, the digital driver has 6-bit digital control signal to change the gate current. And inside the digital gate IC, the PMOSFET and NMOSFET are parallelly connected. Actually, 63 PMOSFET and 63 NMOSFET are parallelly connected to control the IG with 6-bit digital control signal. And by using this digital gate driver, the gate current is dynamically changed by using software. So this is the turn-on transient. So during the turn-on transient, gate current is dynamically controlled by using software. So this is the advantage of digital gate driver IC. And this slide shows the operation principle of conventional and proposed gate driver. In the conventional gate driver, the gate resistance is by tuning the gate resistance RG, the gate voltage waveform is controlled. And this is basically, this waveform is determined by RC time constant. In contrast, in the proposed digital gate driver IC, this is actually a switched current source. So by changing the number of turn-on PMOSFET, the gate current IG can be digitally controlled. In my presentation today, NPMOS means the number of turn-on PMOSFET. So in this design, the 63 PMOSFETs are parallelly connected. And for example, when the NPMOS is controlled from 0, 37, 24, 5, 36, and maximum, the gate current is controlled like this. As a result, the slew rate of gate voltage is controlled in this way. So this is the operating principle of digital gate driver IC. And this slide shows the conventional trade-off between the switching loss and current overshoot in the conventional design. In the conventional gate driver, when the gate resistance is large, the switching loss is large. However, the switching noise is small. In contrast, when gate resistance is small, the current overshoot is very large. However, the switching loss is small. Therefore, in the conventional gate driver design, the switching loss and switching noise was a trade-off. And in order to solve the trade-off of switching loss and switching noise, the digital gate driver is developed. By using the digital gate driver IC, the switching loss and switching noise are reduced, and this trade-off is solved by using the digital gate driver IC. The reason is when the large noise is generated, the gate current is reduced for a short period. By dynamically control the gate current, the digital gate driver can reduce both switching loss and switching noise. So this slide shows the circuit schematic of the proposed digital gate driver IC. This dotted region is implemented on IC. First, this is a gate terminal of IGBT. So this is a gate current. And by digitally control the gate current, 63 PMOSFET and 63 NMOSFET are parallelly connected, and they are controlled by the 6-bit digital control bit. And power supply voltage for the gate driver and output swing is 15 volts. So this gate driver IC achieved 6-bit digital controls, and as a result, 63 level gate current is achieved. And it is also a clock-based design. And in this design, maximum clock frequency was 25 MHz. As a result, 40 nanosecond step gate current controls can be achieved by using this design. And of course, thanks to the digital gate driver design, the gate current is programmed. As a result, the advantage of this gate driver is a general purpose. General purpose means this IGBT can drive a variety of power devices, including IGBT with different current rating. Also, this IC can drive SiC MOSFET. So this general purpose is very important advantage of digital gate driver IC. So common IC can drive a variety of power transistors. This slide shows comparison with conventional gate drivers. Compared with previous works, this gate driver IC can drive a variety of devices, and time and clock-based controls is achieved. And the number of drivability levels is largest, and the tuning range of the gate current is 3 milliamps to 5 amps. So this is the advantage. So this wide range and small time step is the advantage of this gate driver IC. And next, I'll explain the new problem of the digital gate driver IC. Digital gate driver has a lot of tunability because it is digitally controlled with multiple time steps. So this figure shows an example of digital gate driver. In this case, NPMOS, number of turn on PMOS, is controlled with four time segments. In this case, one time step is 160 nanoseconds, and 4 time segments are controlled by the gate vector of N1, N2, N3, N4, and maximum. And in my presentation today, the number of turn-on PMOS or turn-on NMOS are defined as gate driving vector. N1 is an integer between 0 and 63. In this case, we have a freedom of N1, N2, N3, and N4. So as a result, the number of combination of N1 to N4 is 64 to the power of 4. That means 70 million combinations. So we have a huge freedom. So it is very difficult to find the optimum gate driving vector to minimize switching loss and switching noise. And it is impossible to do a simulation or measurement for the 16 million combinations. So in order to find the optimal gate driving vector, we use a software optimization algorithm. In this case, simulated annealing algorithm to find the optimal gate driving vector. As a result, 200 iterations are required to find the optimal gate driving vector. And in this study, we use the measurement to find the optimal gate driving vector because the good model of IGBT was not available for IGBT. So this slide explains the object function for the optimization for the gate vector. Object function is defined as F object. And this equation shows the definition of F object, the turn on and also turn off. The right figure shows example of F object for the turn on. Vertical axis is switching loss and horizontal axis is switching noise. By using this equation, the F object is defined, and the design target is to reduce F object. Small F object means a small switching noise, small switching loss and small switching noise. So the software try to find the optimal gate driving vector to minimize F object. And this one shows the measurement setup to find the optimal gate driving vector for IGBT. We use a commercially available IGBT module. The rating is 600 volts and 100 amps. And this is our developed gate driver IC. We use a 180 nanometer BCD process to design the gate driver IC. Here is 63 NMOSFET, and here is 63 PMOSFET. And this is a controller circuit. This IC is connected to the IGBT. And these are the control signal for the digital gate drivers. The gate driver IC is connected to the low side of the IGBT. And VCC was 300 volts. And we did a double pulse test to evaluate the switching loss and switching noise. This is the measurement setup for the switching test. This is an example of inductor and capacitor. The size is pretty big for the IC designer. And this slide shows the measurement sequence for the automatic search of optimal gate driving vector. So gate driving vector is given to the digital gate driver IC, and double pulse test is done. And correct current and correct voltage waveform are measured by using oscilloscope. And by using waveform, switching loss and switching noise are extracted. After that, object function is calculated. After that, simulated annealing algorithm will find the next candidate for the next gate vector. And by repeating this measurement for more than 2,000 times, optimum gate driving vector are found. This is a measured result of automatic search of optimal gate driving vectors. In this case, 2,400 measurements are done to find the optimum gate driving vector. This is switching noise, this is switching loss, and this is object function for the optimization. In the beginning, the F object is large, and finally F object is reduced. Small F object means the optimization was successful. As a result, switching noise and switching loss is minimized by the optimization. And for this measurement, it takes 15 minutes for the measurement to find the optimal gate driving vector. So this is the period for the measurement for the optimization. You can see the measured waveform is changing. This is an example of measurement to find the optimum gate driving vectors. So this slide shows the measured result of the switching loss and switching noise. This is the important result. And the measurement condition was 300 volt and 50 amp. So in the conventional gate driver design, when the drivability changes from 0 to 1, the switching loss was maximal. However, the switching noise is minimal. In contrast, in the conventional drive, when the drivability is maximal, the switching noise is maximal. However, in contrast, the switching loss is minimal. And in the proposed digital gate driving, this means a red triangle. In this design, the switching loss is reduced by 47% at the fixed switching noise, and also the switching noise is reduced by 37% at the fixed switching loss. So this is the advantage of digital gate driving. Switching loss and switching noise is reduced. And this is a obtained gate driving vector. By using software, the optimal result is 23, 16 to 52 and maximum. So this vector achieved the small switching loss and switching noise. I think the gate vector of 2 is very important because the small gate vector means a small gate current. That's why the switching noise is reduced. So this slide shows the comparison of the conventional gate driving and proposed gate driving. Conventionally, the gate drivability is changed from 0 to 8. In this case, large switching noise was observed. In contrast, in the proposed scheme, the gate drivability is changed in this way. As a result, the switching noise is reduced by 37%. And in this waveform, the switching loss are the same. So as a result, at the same switching loss, the switching noise is reduced. And next, I'll show you the optimum gate driving vector. the optimal gate driving vector is always optimal? The answer is no. Unfortunately, no. Actually, the optimal gate driving depends on the temperature or load current, or also the variability, threshold voltage of IGBT. In order to practically implement the digital gate driving technique, lookup table of the optimal gate driving vector is required to reduce the switching loss and switching noise at different operating conditions, including different temperature, different load current, and threshold voltage variation. Also, the major result of the temperature and load current dependence of the optimum gate driving vector. This is a measurement setup to change the temperature of IGBT. IGBT is put on hot plates to change the temperature. The left figure shows the optimum gate driving vector obtained in the measurement at turn on of IGBT. This graph shows N1, N2, N3, N4 optimum gate driving vectors. As you can see, by changing the load current from 20, 50, and 80 amps, and when the temperature is changed from 25, 75, and 125 degrees, the optimum gate driving dramatically changes. So, in order to obtain the minimum switching loss and switching noise, the gate vector should be changed. And when the optimum vector at some condition is reduced to another condition, the result wasn't. This doesn't work well. In this case, this vector is obtained at 50 amp and 25 degrees. So this is a major result. In this case, the black line shows the conventional gate driving, and red square shows the optimum gate driving. In this case, small switching loss and switching noise is reduced. And when this gate vector is reduced to 8 amp and 125 degrees, the result is not good. And the result is similar to the conventional gate driving. And when the gate vector is re-optimized at this condition, the result is good. So in conclusion, the optimal gate driving in one condition cannot be reduced to another condition. This is an example of major waveform. So this is good result. Gate vector optimized for this condition. This is major result. This is good condition. And when this vector is reduced to different conditions, large current overshoot is observed. However, the gate vector is re-optimized at this condition. The gate switching noise is reduced. So in this way, the optimal gate vector cannot be reduced. And this digital gate driver IC is applied to the three-phase inverter. This is a collaboration result with Professor Wada of Tokyo Metropolitan University. Professor Wada developed the three-phase inverter of 5 kilowatts, including 6 digital gate driver IC, and he developed the inverter system with the digital gate driver. And in his design, the gate driving vector was changed depending on the load current in the inverter. Next, I'll show you the EMI topic. I'll explain the gate driver design to solve the EMI problem. So this is a general introduction of EMI problem in power electronics. EMI is a troublesome problem because the EMI measurement is done after the final product of power electronic equipment is completed. And this is the example of EMI problem. So measure the spectrum violates EMI regulation. So this is the EMI problem. When the EMI violation was found, the two types of solution can be choose: software-based solution and hardware-based solution and software-based solution. Next, I'll show you these two solutions. In the hardware-based solution, typically EMI filter or EMI shields are added to the power electronic equipment. And hardware-based solution will increase the cost and increase the development time. So this is not good for the product development. So in my talk today, I'll propose a software-based solution for the EMI. In this solution, digital gate driver IC is used for the program hardware. And by using program hardware, the EMI is fixed by using software. So this technique is good because the EMI can be fixed after the power converter are finished. And only by tuning the parameter of the gate driver by using software, the EMI problem can be solved. As a result, this is low cost and quickly solves the EMI issue. This shows the conventional approach and proposed approach. In the conventional EMI solution, a lot of work focuses on time domain information. That means voltage waveform or current waveform. In the conventional rise time or fall time or derivative of voltage waveform are controlled. But the problem of the conventional work was by controlling the time domain information, we are not sure if the waveform passes the EMI regulation or not. And it also and in the digital gate driver IC, the manual parameter tuning of digital gate driver was required. So it also takes time. So in my talk today, I will propose a frequency domain evaluation to solve the EMI issue. Because EMI regulation is determined by the frequency domain, so I propose the EMI evaluation and gate driver parameter optimization by using the frequency spectrum. By using the frequency domain evaluation, we can easily know this path and this power converter pass or violate EMI regulation. And by using software, automatic parameter tuning is achieved. So that means automatic EMI problem is automatically fixed. So that is the advantage of this proposed scheme. So I will show the detail on the proposed EMI solution by using the digital gate driver IC. So in this design, in order to obtain the frequency spectrum, we measure the VCE waveform by using Dowd pulse test. And by using measured waveform and repeating the waveform and by using FFT, the CE frequency spectrum was obtained based on the measured data. And by comparing the EML regulation and measured spectrum, we can judge it violates the EML regulation or not. And this slide shows how to optimize gate driving vector to pass the EML regulation. Basically, the optimization loop is similar to the previous work. So the gate driving vector is given to the gate driver IC, and switching loss and AXS is measured. AXS is an area that exceeds the EML limit. So the yellow region is defined by AXS. And by using the measurement, E loss and AXS is measured. After that, object function is defined by using differentiation. And simulated annealing minimizes F object. By using this scheme, AXS is reduced and also the switching noise is reduced. And in this design, C1 is a constant, and C1 was very large. For example, 10,000. So by using this object function, AXS is 0, and 0 means past EML regulation. And in this study, two types of EML regulation is assumed. This is virtual EML regulation. EML regulation A and EML regulation B. This is the measured result of the gate driver to satisfy the EML regulation. The right figure shows the EML spectrum, and black line shows the EML limit. The green line shows the conventional gate driver design with a maximum drivability. The green line violates EML regulation. In contrast, blue line shows the conventional gate driver design that passed EML regulation. In this case, switching loss was 0.83 millijoule. And red line shows pulse design by using the digital gate driver. In this case, red line also passes the EML regulation. In this case, the switching loss is 0.65 millijoule. As a result, by using this optimization scheme, the switching loss is reduced by 22%, with satisfying the EML regulation. This is a measured waveform. Both satisfy the EML regulation. This is conventional design. Step driving by using 8. And this is a proposed digital gate driver design. In this case, 8 times step was used to optimize the gate driving waveform. By using this scheme, the switching loss is reduced by 22%, and both satisfy the EML regulation. So this is the advantage of this scheme. And this is also another example in case of EML regulation B. In this case, in the conventional gate driving, by using the weak gate driving of 5, the blue line satisfies EML regulation. However, the red line shows the proposed scheme. Only the proposed scheme can satisfy EML regulation. So by using the digital gate driver, the digital gate driver can achieve the better EMF performance compared with the single-step gate driving. Okay, I'll move to the next topic. Next topic is machine learning, power device degradation IGBT by the machine learning of gate waveform. The reliability of power devices is very important because the power converters are used in a critical application, including the industrial and automotive application. And in my talk today, machine learning is applied to estimate the reliability of power devices. In my talk today, I tried to estimate 4 parameters to determine the reliability of power devices. RE is the emitter resistance of IGBT. TJ is the junction temperature of IGBT. IC is the correct current of IGBT. And VTH is the threshold voltage of IGBT. And in my talk today, conventionally, to measure the 4 parameters, various sensors are required. To sensor IC, current sensor is required. To measure the VCE, voltage sensor is required. To measure TJ, temperature sensor is required. To measure RE, voltage and current sensor is required. So it will increase the cost. So to solve the problem, we propose a gate waveform monitoring because it is easy to measure the gate voltage because the amplitude is less than 15 volts. So only by measuring the gate waveform and by using machine learning, these 4 parameters can be estimated by using machine learning. So to estimate these parameters, temperature sensor, current sensor are not required. So it will reduce the cost for the sensors. So to check our concept, we need a spice simulation and measurement. So this is the setup for the spice simulation. In the spice simulation, the 4 parameters are changed as shown in this table. And parameters are categorized into 5 classes, 0, 1, 2, 3, 4. And gate waveform is obtained by using spice simulation. And by using these 4 parameters, 110K waveform are obtained by using spice. And we use the convolutional neural network for the machine learning to estimate the 4 parameters, the gate waveform. And this figure shows the classical CNN network, length 5. This is developed for the image recognition. And this length 5 is modified gate waveform of the machine learning. And this is the CNN network for the machine learning of gate waveform. Gate waveform is one-dimensional input, voltage, and time in time domain data. So input vector is 500 by 1. And by using 2 convolutional networks, the final output is 5 or 6 classes. So this is a simple convolutional neural network for the estimation of the reliability parameters from the gate waveform. And this is the simulation result for the estimation of 4 parameters. The blue numbers show the success rate in the simulation. For the correct current, TJ and threshold voltage, success rate was 100%. And in case of emitter resistance, the success rate was 98.3%. The result was pretty good. So next, I'll show the measured data for the estimation by using machine learning. In the measurement, correct current and emitter resistance are changes in the measurement. And to change the emitter resistance, we change the resistor of 6 types. The left photo shows measurement setup. And this slide shows the measured gate waveform with different correct currents and different gate resistance. So each waveform includes 6 waveforms with a different gate rate. So this slide includes more than 66 gate waveforms. And so they are the input to the machine learning. Machine learning run by using this data. And after that, machine learning estimates the emitter resistance or correct current. And this table shows the measurement classes for the emitter current and also for the correct current. The number of classes are 6. The number of measured waveforms are 6,600. So this is the result for the estimation result by using measurement. For correct current, the success rate was 100%. It was pretty good. And for emitter resistance, the success rate was 99.5%. So overall result was pretty good. So for the emitter resistance, the correct current was estimated by using gate waveform. Okay, I'll move to the final topic. I'll introduce the very high data rate digital isolator, IC. As you maybe know, digital isolator is an important block to isolate between the low voltage domain and high voltage domain. For example, in the high side of the gate, high side of the converter, the source voltage of VSS changes between 0 volt and 600 volt. However, the controller gives the control signal with 5 volt. So there is a large voltage gap between the low voltage domain and high voltage domain. Therefore, the signal isolator is required for the communication between the controller and the power converter. And conventionally, the gate driver was very simple. Only turn on and turn off. Therefore, the information was only 1 bit. But in the design of digital gate driver, the information will increase. For example, 6 bit and 6 bit data for every 25 nanoseconds. So a lot of data is required for the digital gate driver. So in this case, our design target was 240 megabps to achieve this data for the digital gate driver. However, in the commercially available digital isolator, the maximum data rate was 150 megabps. So our design target was to achieve the 500 megabps for the next generation signal isolator. So this is the overview of the digital IC. The on-chip transformer are implemented on die. The on-chip transmitter, the diameter is 250 micrometers, and transformer is achieved between the metal 5 and metal 1. And transmitter and receiver chip are achieved with different die. And transmitter die and transformer is connected by using bonding wire. And this slide shows the problem of conventional 500 megabits digital isolator. In this conventional design, the counter pulse should cross the threshold voltage. I'll skip the detail of this timing chart. Anyway, in this conventional technique, the maximum data rate was 250 megabits. And in order to solve this problem, we propose a new signaling scheme for high data rate. So the transmitter pulse is reduced to increase the data rate, and we develop a new receiver circuit to detect the voltage pulse for the short TX pulse. And as a result, high data rate was achieved. And this is a detailed receiver circuit schematic of the receiver. I'll skip the detail of the circuit design. But anyway, to receive this kind of voltage pulse, we design a new receiver circuit to receive the short pulse. And this is the die photo of the developed digital isolator. The left die is a transmitter chip, and the right side is a receiver chip. And you can see the on-chip transformers. Diameter is 250 micrometers. And we use a 5 volt and 1.8 micrometer CMOS process for the digital isolator. And this slide shows the comparison of digital isolators with previous work. Commercially available isolator is 100 megabps, and previously published paper achieved 205 megabps. In contrast, we achieved 500 megabps with a diameter of 250 micrometer on-chip transformer. And simulated CMTI was 130 kilovolt per microsecond. Okay, this is the talk. Today, I introduced the digital gate driver IC. And this IC is a key block to enable the power electronics 2.0, including IoT and AI. And I'd like to thank my collaborator from University of Tokyo and Professor Wada from Tokyo Metropolitan University, Professor Obara of Yokohama National University, Professor Manne of University of Tsukuba, and Professor Omura of Kyushu Institute of Technology. So this is joint work between different universities. And here is a reference for my talk today. Okay, that's it. Thank you so much for your kind attention.